Responding to your request for lecturing about intermolecular forces. First off, I hope you guys are doing okay. I don't know about y'all, but I'm getting a little bit stir crazy myself. This is actually kind of keeping me a little bit occupied. Let's get started with a little bit of information about the liquids and intermolecular forces. This is the first state of matter that we study after gases. These guys, we'll talk about gases a little bit later on. We do need to focus on the intermolecular forces themselves because they're a topic that does pop up in your IB book. Let's begin here today. Biggest difference between the states of matter is the distance between the particles. That's actually what defines what the state of matter actually is. How close a particle is determines whether or not it's going to be a solid, a liquid, or a gas. In a gas, these guys we study first in your freshman year. These guys are super far apart. They have a lot of energy, and they actually don't have very strong intermolecular forces. There's almost no force of attraction between the molecules of a gas. Once we condense them and we lower the amount of energy, the particles become a little bit closer together. Once we reach the liquid phase, the very, very minute forces we're about to study begin to attract to one another, and we can get different properties of a liquid. We're going to investigate these individual properties here between the individual molecules and how they interact and what they actually are. They also exist in a solid. In the solid, we've lost so much energy that they are essentially locked into place. They only vibrate a little bit, but there are still these intermolecular forces present within a solid. Now, in a solid and liquid states, the particles are very, very close together, so we often refer to them as simply the condensed phases. These guys do function quite a bit differently than gases. The way they function makes them a little bit harder to study on a molecular level. So, the state of matter that a substance happens to be in is depending on two antagonistic entities. We have two things actually kind of working against each other for the state of matter at a specific pressure and temperature. The first off is the kinetic energy of the particles. This is the energy of the particles actually moving. The particles kind of want to move away from each other. That may not happen depending on what forces of attraction are between the molecules. So we have these two fighting together, and how a substance behaves determines on how much energy, how much movement, kinetic energy it has, but also the strength of the intermolecular forces we're starting to study. These forces are not as strong as a full molecular bond. If it was, they would not be called intermolecular forces, but intramolecular forces. These molecules and these forces here, the bond is weak and it is not strong enough to make a new compound, or else we'd have another chemical reaction. But they can make the compounds kind of stick together. They also influence the physical properties of the substances. Things like the boiling point, the melting point, the viscosity, all of those things together are influenced by the minor force of attraction between molecule and molecule. Together, all of this group of forces is known as van der Waals forces, and there are many different kinds out there. The ones we're going to study first are dipole-dipole interaction, and these involve polar bonds. Hydrogen bonding, this is an extremely strong function. And then also London dispersion forces. London dispersion forces we're going to find everywhere, and every single atom molecule absolutely has London dispersion forces. That's a good starting point for investigating these. London dispersion first. This is ultimately the alignment of the electrons. If you take a relatively simple molecule, for example, here we have two individual atoms, and the electrons are spinning around. Every so often, through pure coincidence, they happen to line up on one side. And that creates a slightly negative end and a slightly positive end. And so the interesting thing about this is that it can actually induce another polar atom in a neighboring atom, and they can be forced to line up. And then it kind of changes from atom to atom to atom, and they briefly come together again. So, at that brief moment of alignment over here, we have these two electrons temporarily on one side of the atom. We end up with a slightly negative side and a slightly positive side. That can induce a dipole moment in another atom. Atom B was originally the one that lined up with its electrons on one side, and all those electrons force atom A's electrons to the opposite side. Atom B's electrons are attracted to the positive proton core. The electrons on atom A are pushed off to the side. Now, if there were other electrons and other atoms that were chained over here, they'd all go in a chain reaction. Now, this temporary attraction ends immediately when any electrons move, so it's very, very brief. But at the same time, they can also, again, randomly line up. So this ultimately is a random alignment of electrons. These are called London dispersion forces. This is the attraction between that instantaneous dipole moment and an induced dipole moment between two atoms, and they can chain between atom to atom to atom. These forces, these London dispersion forces, are present in every molecule, in every atom, whether or not that molecule is actually polar or not. Everything has them because they have electrons. The tendency for an electron cloud to distort and to shift to one side is called polarizability. And this is based on a few factors. You can predict who can randomly have their electrons line up more often than one or another. So, a few factors that can affect this random alignment. One of the biggest factors happens to be the actual shape of the molecule. Long, skinny molecules have a higher surface area, and that means that there's a higher chance that the random alignment of electrons is going to happen anywhere along that electron. Short, fat molecules, even with the exact same formula, they have a lower surface area. Whenever they get sticky and they have that random alignment, there's very little area for them to brush across another molecule. So if I have a short fat molecule right here with another short fat molecule, the point of contact is very small. They kind of slip right past each other. On the other hand, if I have two long molecules, the surface area is very great, and anywhere along that point of contact we could have a brief attraction of electrons. That extra area of contact is why long, skinny molecules tend to have greater London dispersion forces. The weight of the actual molecule or the atom is also increasingly important. And this is because that electron clouds are bigger in bigger atoms or bigger molecules. The bigger the electron cloud, the more electrons you have. This is merely a matter of probability. The more electrons you have, the greater chance that any of them might randomly line up. A second force, and one that we're a little bit familiar with, is dipole-dipole interactions. This is a permanent positive and negative end among a polar molecule. And these permanent and positive negative ends become attracted to each other. We're very familiar with this in how water behaves. That whole running joke of whether water is wet, oh, that's actually this interaction right here. If this happened to be a water molecule and the oxygen being very, very negative and the hydrogen being very, very positive, a water molecule permanently exhibits two opposite ends. The whole charge does cancel out, but they can be attracted to opposite ends, but also repulsed to opposite ends. So we end up seeing the positive end attracted to the negative end of another element and vice versa. These forces really only come into play when the molecules are close to one another. This also includes the London dispersion forces. If they are too far apart, in other words, they reach the gas phase, these forces really don't have any significant impact anymore, really only present in liquids and solids. This means we can start predicting boiling point, melting point, and a few others. For example, the more polar the molecule, the higher the boiling point. We start over here with propane, for example. Propane has an atomic mass of 44. Dimethyl ether is 46, acetaldehyde is 44, and acetonitrile is 41. Their molecular weights are nearly identical. The shape of the molecule is nearly identical. They're almost all linear molecules. The biggest difference here is the presence of very electronegative elements and where these electronegative elements are present. Propane tends to have a very low boiling point, only 231 Kelvin. That's really close to 0 degrees Celsius. It's nothing but a bunch of carbon and hydrogen. When you replace one of the carbons with an oxygen in dimethyl ether, you begin to create a polar molecule, an uneven pool of electrons. Here, the electrons prefer to pull upwards towards the oxygen and away from the other carbons. If you change the location of the oxygen to the end of the molecule, you create an even more polar bond. And finally, if you replace the oxygen with a very electronegative element like nitrogen, you can end up with an extremely polar molecule. The electrons prefer to be located all the way around here on the nitrogen and away from the rest of it. This creates a very, very strong polar bond, and that strength will attract other elements and compounds even stronger. The higher the strength of the dipole interaction, the higher the boiling point. And simply put, the atoms and molecules don't want to be put away from each other. It's like a really strong magnet. It takes more force to pull them away. Thus, the boiling point is even higher. So, what actually has a greater effect? Well, there's a few things that we can look at. One is not inherently stronger than the other. We have to compare a few things. If the molecules are of comparable size and shape, the dipole-dipole interactions are probably the dominating force. Now, that means polar bonds, if present, will probably be stronger if everything else is equal. They have the same molecular weight, they have roughly the same shape, like in the previous example. If one molecule is physically larger than another, it has a larger atomic mass. Well, a larger atomic mass means that it happens to have more electrons. Then it's probably likely that the London dispersion forces, that random alignment of electrons as they kind of line up together, is probably going to be the determining factor for its physical properties. So we need to examine all things about the molecule. So how do we explain what's happening over here? This is a nonpolar series. For example, tin hydride to carbon hydride. And we see here the carbon hydride to tin hydride. This little odd thing right here doesn't seem to follow the standard trend of water, hydrofluoric acid, and NH3. What's that going on right here? This is a nonpolar series and acting a little bit odd. This guy follows a trend until you get to the smallest atoms in the group, molecules, all the way down here at CH4. Unlike the other groups, group 7, group 5, and group 6, once you reach the smallest molecule right here, the CH4 happens to drop its boiling point. That's a little bit unexpected. Normally, if we were to follow the pattern and trend here, we would expect the CH4 to have a very large boiling point. That's not happening. This is actually the result of a final force known as hydrogen bonding. This is extremely powerful and extremely unique. Hydrogen bonding is just another dipole-dipole interaction, another polar bond, but it's very specific. It only occurs when hydrogen is bound to nitrogen, oxygen, or fluorine. That's it. No other interaction is as strong as hydrogen bonding short of an actual molecular bond. These guys are so strong we have to give them their own name. We call them hydrogen bonds. But they are still technically just a dipole-dipole interaction, a permanent polar force attracted to another molecule. This happens because of the function of hydrogen. Hydrogen itself is actually very, very simple. It is just one proton and one electron. And when you combine it with the extremely high electronegativity of nitrogen, oxygen, and fluorine, they act like bullies. They pull hydrogen's electron onto themselves. And essentially, you get an exposed proton core, a very, very strong positive with nothing to mute it and nothing to diminish it. So you get a very, very, very strong positive end due to the electron practically being ripped away off of hydrogen and onto nitrogen and oxygen fluorine. There is actually a fourth type of force. These are not really considered officially van der Waals forces, but they are intermolecular forces themselves. This is when we have an ion dipole interaction. We already know about ions. For example, sodium metal, when it loses electrons, becomes sodium ions. Same thing with magnesium metal, becomes Mg plus 2. This is what happens and this is the interaction for why salts dissolve in water, for example. Water is a polar molecule. It has a bunch of positive and negative ends. And water, when it comes into contact with sodium chloride, NaCl, will surround the individual atoms of sodium. The negative portion of water will be attracted to the positive sodium, and then we see it rip it off the cube and it dissolves. The positive portion of water, the hydrogen, will be attracted to the negative portion of the chlorine, and they'll separate the chlorine from the sodium, causing salts to dissolve. This function, and this is overall called an ion-dipole interaction, but it's technically not a van der Waals force, but it is a fourth new kind of intermolecular force. Summarizing these intermolecular forces, how do you know what is present? Well, the first thing you can ask yourself is, are there ions present? That answer is no. A lot of plain molecules do not have ions present. Then you're probably dealing with the standard van der Waals forces. Then you ask yourself, is this a polar molecule? you are going to need to draw the structure and go through the Vesper modeling to determine whether or not something is polar. Remember, in a polar molecule, you have an uneven pool of electrons in the 3D molecule. Don't forget to visualize what the molecule looks like in 3D. If there are no polar molecules present, then there simply is no dipole-dipole interaction. You have the most basic force present, London dispersion forces, random alignment of electrons. If you do have polar molecules present, then you have to do a quick check to see whether or not there is hydrogen bonding. Hydrogen bonding is extremely strong, but also very narrow. It must be hydrogen combined to nitrogen, oxygen, and fluorine. If that's not happening, then you have standard dipole-dipole or polar interactions. Finally, if you do have hydrogen bonding, they are considered van der Waals forces. It's just a special kind of dipole-dipole interaction. Now, if there are ions present, you have to be a little bit careful. Here, we have to ask ourselves, are there polar molecules present in the mixture? More than likely, you're going to have a mixture of molecules and ions, like water and salt. If that's happening, then you have an ion-dipole interaction, like salt dissolving in water. And that's what we saw in the previous example. If there are no polar molecules present, then what you have here is a case of ionic bonding. This is actually at this point no longer considered an intermolecular force. On ionic bonding, it's so strong it actually is a separate bond itself, and you have a chemical reaction happening. And that is essentially the dividing line right there between intermolecular forces and a full bond. This is where I'm going to stop here for a moment. I will talk about the factors that can affect the intermolecular forces a little bit later. There are things that can influence these and also change how a solution behaves. Right now, this is a good start for the initial work that I gave you this week. I hope you guys take care of yourself. Practice social distancing. I know we're all tired of that. But currently, the cases we have in Nueces County, I think there are 6 or 7 now. Every single one of them was a person who traveled. For the moment here, hunker down, try to do something, keep up a routine, and we'll get through this. Y'all take care. Let me know if you have anything. I'll see y'all hopefully in a few weeks. If not, I'll see you all in a few months.